Good morning, everyone. We're going to go through and do a walkthrough of evidence assignment 14, a second roller coaster problem. So we are doing a simpler problem here today. I have a feeling that some people will benefit from this, but remember there is a trade-off. If I do a simpler problem that only concerns itself with one target, it means it's harder for me to give you more evidence. So I can only give you credit for an evidence assignment for target 8.1 on this. Whereas I've been trying to do ones where I can give you multiple pieces of evidence for one problem. So that is the trade-off we have. But anyhow, let's go through this. I'm hoping that with a little bit of help here, you guys will be able to see these energy problems are relatively, they honestly are a lot easier than a lot of the stuff we've been doing all year. So we have a roller coaster here, and we're told the height of the roller coaster. At this moment right here, they're not moving, or at least they have to be moving a little bit, right? Or else they'll just stay there forever. But it's about 0. And then here at point B, they're at the top of this loop. It's 30 meters in the air. Here at point C, they're 20 meters in the air. And ignoring friction, we want to first start off with an LOL diagram. So let's go ahead and do that. So L for A, and then we'll just copy that. All right. So this will be at point A, this will be at point B, this will be at point C. We'll draw the O's in here. So at point A, not moving. So EK is 0, but I'm pretty sure that's going to be moving here at B, pretty sure it's going to be moving here at C. So I'm going to go ahead and put in a column for EK, but column A is not going to get anything. Or an LA is not going to get anything. At point A, I'm pretty sure all of the energy is being stored gravitationally, so we will start there. Let's just go ahead and dump a bunch of energy gravitationally. So I don't know how many you guys want to do. Maybe 3 or 4 or 5 or something. Let's just do. Let's do 6. I think that'll work. Now at point B, some of this energy is still stored gravitationally. You look here, we're still 30 meters in the air. In fact, it's like half as high. So I'm actually going to keep half of this in here. So we'll just take these 3, and we'll keep those in there. But the other 3 are gone. So presumably the other 3 are just now here. Like the cart's moving now, right? So now half of the energy is stored gravitationally, half of the energy is stored kinetically. And then finally at point C, we have 20 meters. That's a little bit even lower. So presumably a little bit more energy has now moved over. So I'm just going to go ahead and copy all of this. Move it over here. But then we'll move this one box right here over to here. All right. So I think that's a pretty reasonable description, right? We have a bunch of energy stored gravitationally, and as we go downhill, more and more and more of that energy gets stored kinetically. Don't let the fact that this is a loop freak you out. You're still just going uphill. So this must still just be stored kinetically, still stored gravitationally. There's nothing too fancy here. Now, it does say there was no friction. We are ignoring friction here. If there was friction, remember friction causes change in temperature. Friction causes energy to be stored thermally, but we'll ignore that for the time being. So that's number one. Part two, predict the speed of the carts at point A, B, and C. So here's what we're going to do. I'm going to go ahead and make equations for what we have here. Here, all of our energy is stored gravitationally. So all the energy is stored gravitationally. That's 6 boxes. Well, here we have 6 boxes, but that 6 boxes is split up. It's split up between EK and EG. And here we have 6 boxes split up between EK and EG. So we can go ahead and start figuring this out. We know that the energy stored gravitationally can be found by taking the mass times our 10 newtons per kilogram times however high it was, the height. And we'll end up using that for all of these EGs. So mass times 10 newtons per kilogram times the height. Mass times 10 newtons per kilogram times the height. But then now these two both have the energy stored kinetically, and that's just 1/2 the mass times the velocity squared. Yeah, so this should be true. So for this energy stored gravitationally in point A, that'll be equal to the sum of these two energy storage systems at point B and at point C. So let's go ahead and just start plugging stuff in. I know that the mass of the cart, let's go find it, 300 kilograms. So everywhere there's an M is 300 kilograms. By the way, side note, I'm going to pretend I didn't notice this, but if you noticed that all of these M's, like there's an M in every single term here, that means you can actually cancel the M out. The mass doesn't actually affect your answer here. Just FYI. Oh, but it will actually affect this last one, so be careful. But for this, so I'm just going to ignore that for right now. So the mass is 300 kilograms times 10 newtons per kilogram times the height, 60 meters. That'll be equal to 1/2 300 kilograms times whatever velocity it gets to squared plus 300 kilograms times 10 newtons per kilogram times 30 meters. We'll go ahead and ignore this one for right now. We'll come back to that in a second. Let's just go ahead and solve this one for v squared. So 300 times 10 times 60. 300 times 10, oops. I get 180,000 joules. All right, that'll be equal to, well, 1/2 times 300 is 150 kilograms times the velocity squared. We'll be solving for that in a second. Plus, well, this is interesting. So I know that this is 300, 10, and 60. Well, this is 300, 10, and 30. I mean, I could just throw that in my calculator, but I see that the 30 is half as big, so I'm just going to make this half as big, 90,000 joules. If these two things are equal, I'm just going to go ahead and subtract 90,000 for both sides. So that means 90,000 joules is equal to 150 kilograms times our velocity squared. Divide both sides by 150. So I'll end up getting that the velocity squared is 600. So that means our velocity, we'll just go ahead and take the square root of both sides and get 24.49. So here at point B, we are going 24.49 meters per second. Excellent. So I'll go ahead and write that up here. The velocity here is 24.49 meters per second. If you'd like to, you can round that down to 24 meters per second. That'd be fine by me. All right, we'll do the same math here, but now for point C. In fact, I'm literally going to just copy and paste all this and just replace the 30, because that's the only thing that's different, right? We still have the same starting energy, and we still are going to have the same expression for EK. The only difference now is we're at a different height. So I'm just going to literally copy and paste this whole thing. But then we've just gotta put in a different height. Oops. Come on, you. Just put in a different height. Whatever. So the new height now is 20 meters. So now we're just going to solve this for v squared. This still works out to 180,000 joules. This one, I know that this is a third the height, right? So 60, 20, that's a third the height, so that should be a third the energy. This will only be 60,000 joules. So this 1/2 times 300 kilograms times v squared plus 60,000 joules is 180,000 joules. That means this must be 120,000 joules. I'm going to go ahead and get the v squared by itself. So to do that, I'm going to divide it by 300 and multiply it by 2. I end up getting that v squared is equal to 800. Which means that our velocity, once we take the square root of that, I get 28.2. For those of you math nerds who are doing, who go, well, this should be plus or minus. Yeah, that's totally true. It doesn't actually matter what direction we're going. It could be plus or minus. We just know that the overall speed has to be 28.2. The magnitude of this number, the absolute value of this number has to be 28.2 in order to give us the energy that we need. Anyhow, so here we should be have a velocity of 28.2 meters per second, and yeah, I'd let you round that to 28. So good. Congratulations. If you've gotten that far, you've done the hardest stuff in this problem. So just a quick recap before we move on. So the roller coaster starts out at the top of the hill, then starts moving down the hill, and then gets further down the hill. But as it goes down the hill, it speeds up, because the energy that was stored gravitationally starts being stored kinetically, and that keeps going as it goes downhill. We then figured out the mathematical expressions that fit along with this. So the energy stored gravitationally and kinetically, energy stored gravitationally and kinetically. And then we started plugging things in to find the missing values. We ended up doing the math to solve these, and you notice the math looks almost identical. The only difference here is we're at 30 meters. The only difference here is we're at 20 meters. All right, so let's figure out everything we did wrong. Uh-oh, the cart's only going 20 meters per second at point C. Boo, right? Something happened. I guess there was friction. Draw a new L for point C to show what happened. So let's figure out what's going on. So this is my L that I was using for point C, but the cart's not going as fast as we thought it would be. It's going slower. So here's what I'm going to do is I'm going to go ahead and I'm just going to make a new version of point C here. Sorry. Make a new version of point C here. Get rid of this little extra L, and then we'll put a little mark. This is the new version of C. So we know that we don't have as much kinetic energy as we thought we did, right? These two boxes aren't really there. They must be somewhere else. We're pretty good on height, all right? The height didn't change. We're not wrong about how high point C is. What we're wrong on is how fast it was going. So these two boxes of energy can't be here, and these two boxes of energy can't be here. They must be somewhere else. Now there's two options, but either one have the same effect. You can either say that this energy just left the system, which is fine. Or what I'm going to do is I'm going to say that this energy was stored thermally. Now, they'll both work out to be the same answer. You just have to go about thinking about it a little bit differently. But it doesn't really change anything. So we have a bunch of friction. That friction is causing energy to be stored thermally rather than be stored gravitationally or kinetically here. The cart is slowed down. And I'm sure if you've ever been down like a slide on a hot day and you know that friction can slow things down. So that's exactly what's going on here. So how do we account for this? Well, let's look here. We thought we should have had, what was it? Here at point C, we can figure out how much energy we should have had, and then figure out how much energy we actually had, and figure out what's the missing energy. Let's figure out how much energy how far are we off? Because if we can figure out how far we are off, we can figure out how much energy is stored thermally. By the way, when we're done, I'll show you how you would have thought about this as far as work goes. So we can think about how much energy is stored thermally. So let's do that. We thought we'd be going 28.2 meters per second. So let's just go ahead. We'll draw our two boxes right here. So we thought we'd be going 28.2 meters per second, but we're actually only going 20 meters per second. So what I'm going to do is I'm going to figure out how much energy did we think we had, and then compare it to how much energy we actually had. So the amount of energy we thought we had was 1/2 the mass times the velocity squared. That'll be for both of these. So that's 1/2 times 300 kilograms times the 28.2 meters per second squared. And then the amount we actually had is 1/2 times 300 kilograms times 20 meters per second squared. So I'm going to go ahead and calculate both of those real fast. We thought we would have 120,000 joules. Oh, I think we already calculated that up here, didn't we? Yeah, we thought we'd have 120,000 joules. See, I should have just remembered that. We thought we'd have 120,000 joules, but we don't. Instead, we only have 60,000 joules. So half of the energy that we thought we'd have is gone. So we have 60,000 joules that's just gone, that's just missing. Where did that energy go? It must be stored thermally. So this energy that's stored thermally, this 60,000 joules, 60 kilojoules, we have to figure out how much friction would happen to cause that. All right, so here's the rule. If we think of friction as work, right? Friction, when you move against friction, that is work, which is, by the way, the tact you'd take if you want to say this was energy was just leaving the system. It's just work. Well, work is always equal to the amount of force you're pushing against times the distance that you're traveling. So if we know how much energy got lost this way, we can tell that must be our force of friction times the distance we've traveled. We're told in the problem that the actual length of the track is 170 meters. So the force of friction acting on this cart, on average, you had to push the cart through that friction for a total of 170 meters. And when you did that, you ended up storing 60,000 joules of energy thermally, or you could think of it as doing 60,000 joules of work, either way. But we should be able to solve this for the force of friction. The force of friction then will be just equal to the 60,000 joules divided by 170, which I get 353 newtons. So So on average, at all points here, the amount of friction being applied to the car is 353 newtons. Now, I imagine if you go become a structural engineer and start designing roller coasters, you probably have some more sophisticated ways of describing this. So, for example, like the track flexing will do some work, so some of that energy would actually be going there instead of just straight friction. The internal workings of the cart and things like that will have an effect on this as well. But I think this is a reasonable assumption for a reasonable description for our level of class. All right. So quick recap. I know this has been a long video, but some of you guys really need this, and I don't mind taking the time and covering it all. So quick recap. We have something storing a lot of energy gravitationally. Then it's lost half of this energy stored gravitationally. It's now stored kinetically. And then it's lost a little bit more energy stored gravitationally. It's now kinetically. We went through and calculated the speeds using our expressions for each of those different types of energy. Then what we did is we figured out, oh, we were wrong. We've lost some energy due to friction. That energy is now stored thermally, or you can think of it as work, depending on what perspective you want to take. But either way, we know that the distance you traveled along the track times that force of friction will tell you how much energy we've lost. We found the energy we've lost was 60,000 joules. If it's a 170-meter track, the only way to make that happen is if friction is 353 newtons. All right, everyone. We'll call that good for the day. Please do let me know if you have any questions. I'll also be posting this image as a key. So if you want to see this again so you can look over your homework, that would be great. All right. Have a nice day.